Algebra 2, Chapter 10, Section 6, Exponential Functions and Base e. The number e was first described by mathematician Leonhard Euler and is a fundamental mathematical constant. Mathematical is spelled wrong, sorry. Mathematical constant. Similar to pi, e is a transcendental number. Such numbers have no exact decimal representation, similar to, say, the square root of 2. And it's also similar to the square root of 2. Their decimal representation does not repeat. Furthermore, they are not the solution themselves to any polynomial function. That's different than the square root of 2. The square root of 2, of course, is the solution to a quadratic function, so it's definitely not transcendental. The number e arises in any situation that can be modeled by continuous growth. Every exponential function of real numbers can be modeled continuously, so therefore it is possible to convert any exponential into the form where we have a base of e, a times e to the kt, for constants a and k. So a here is the initial value, which is the same initial value that we had here, but k is what's known as the continuous growth rate. Okay, so you can see b equals e to the k, where e is this number that Leonhard Euler first described. And you might want to know, what is e approximately? So it would be 2.718 approximately, and you can see 281828, and it does not repeat in any way. It's not, like I said, it's non-repeating. 2.718 is approximately what e is equal to. We'll talk later on in the class about why e has this value and where it comes from. But right now, we'll just suffice it to say that it arises when we have continuous growth, and we want to describe growth with a continuous rate that's being applied constantly to a quantity. So equations A through C describe the value of investments after t years. For each investment, give the initial value, the continuous growth rate, and the annual growth factor, and the annual growth rate. So we have several things to describe. As I said before, the initial value is the same for both forms. So the initial value is 2,500. The continuous growth rate is directly described here, e to the 0.035. So 0.035 is a rate. So if we want to describe it as a percent, we can. 3.5% is the continuous growth rate. The annual growth factor would be e to the 0.035, which our calculator can find, e to the 0.035. So here we have e to the 0.035, 1.0356. So 1.0356 is the annual growth rate. Sorry, the annual growth factor. So here is our continuous growth rate k, our initial value a, and now we want to know, what is r, the annual growth rate. Subtract 1 as a percent, it's 3.56%. So it's similar, it's close to the value of k, the continuous growth rate. B, the initial value a here is 5,000. The continuous growth rate is 14.7%. The growth factor b would be e to the 0.147. E to the 0.147 is 1.1584. 1.1584. And r would be 1 minus this, 15.84%. And you can see we're less similar to the continuous growth rate now that the growth rate's bigger. That's generally true. The closer you are to zero growth, the closer the continuous and the non-continuous rates will be. C, 6,250 is our initial value A. K, in this case we are always talking about growth, so our continuous growth is negative 9.5%. Our B would be e to the negative 0.095. So e to the negative 0.095 is 0.90937. 0.90937. 90937. So the R, our annual growth rate, would be subtract 1, negative 10 point something percent. Let's do it with the calculator. Sorry, negative 9.063%. Negative 9.063%. Again, similar to the continuous rate, but not the same. So, to talk a little bit more about this sort of idea of continuous growth, if you imagine a bank account with a balance, and we say we get an annual rate of so many percent, but that rate is compounded monthly, that means every month I actually get the interest deposited in my account. And that monthly rate will be different than the yearly rate. We could convert the yearly rate to a monthly rate by by solving an exponential equation. Well, we could also break that. What if a bank has an annual rate, but they give you the interest every day with a daily rate that gives you the overall yearly rate after a year? And you could break that down into hours. What if they gave you an hourly rate? What if they gave you a rate at every minute? What if they actually compounded your interest every second with a rate that ends up being the same over a year? Well, continuous growth is like compounding the interest on a bank account every billionth of a second, or actually it's really every infinitesimally small part of a second. And the base of that growth is this number e, which is where that number comes from. So let's talk another function that has e in it. It's not exactly exponential, but it contains exponential pieces. So this function defines, really it's an expression, defines a population that starts at 20 and levels out at 80. So if you were to see a graph of this function, it's something like 20, and it goes up pretty quick, but then it levels off like this at 80. It never quite gets to 80. So if you plug in really big numbers here to this equation, you never quite get to 80. You just get really close, is the idea that I believe it means by leveling out at 80. Biologists sometimes write the expression for p in a different form, L over p naught plus a e to the minus kt. Put p into this form and give the values of these constants, L, p naught, and a. Okay, so we need to multiply the original fraction by another fraction that's going to get us into this form. It may not be obvious how to do that at first. We need a negative kt, so let's think about that. If it were negative kt, what if we just multiply, let's just multiply the whole thing by e to the minus kt over e to the minus kt. So what will happen is we'll add these exponents and they'll go away. They'll be 0. E to the 0 is 1, just like anything to the first power is 1. I'm sorry, anything to the 0th power is 1. So e to the kt times e to the minus kt is going to be 1 times 1600 is 1600. Because this ends up being e to the 0, which is 1. And the denominator, we get e to the minus kt times 60 using the distributive law, and we get 20 e to the kt times e to the minus kt. Again, e to the kt times e to the minus kt is going to be 1. because we'll add the exponents, which will make them 0. And we'll have e to the 0 is 1, which is 1 times 20 is 20. So we have plus 20. This is almost in this form. We just need to change the order of the addition. 1600 over 20 plus 60 times e to the minus kt. Okay, so L is going to be 1600. P naught is going to be 20. And A will be 60. That's the answer to the part about identifying the constants. Putting it in the form is answered here.